Let's start. Good morning. My name is Gustavo Patino, and I am at Oakland University William Beaumont School of Medicine. I'm actually a neuroscientist and teach neuroscience there. But today I will be telling you a little bit about the struggles I've had trying to make my run code faster. And this partially stems that a lot of my research interests are in running computational models of neurons or heart cells, and we try to do a lot of differential equation numerical approximation because these are equations that don't have an analytical solution. So before we start, can I have a show of hands? How many of you have tried to do specifically parallel processing in your computer within the Jupyter Notebook? Okay. So, and how many of you have tried to do Cython in general? And within the Jupyter Notebook? Okay. So we're going to be focusing a lot on the Jupyter Notebook. And let me tell you my disclaimers. So because I come from the biomedical sciences, like I have to tell you, I don't have any financial interests. I also have to warn you, I am not a computer scientist, so don't get too hung up on the code if it's like really bad code. And there's a lot of annotations because I have to really write down what I'm doing at every single step. But let's try to just focus on the different comparisons that we're going to make today. And of course, the biggest warning of all, which you already know, is that if I say optimization, you guys say is the root of all evil. So don't do it too fast. Now let me tell you a little, very quickly, what is the problem that we're going to try to solve today with the code. And in doing that, we're going to be able to compare different ways to try to make it faster, again, within the Jupyter Notebook. And let me tell you why I wanted to have this session in the Jupyter Notebook. In the biomedical sciences, we use the notebook as a way, as our lab notebook, to keep track of all the things we've tried, what kind of things have worked, what kind of things haven't worked so much. But what you find is that a lot of the libraries that are out there, their performance within the Jupyter Notebook only allows a subset of those available commands to actually take place. So the idea of the session today is to give you a reference of from those libraries that you have heard, these are the things that really work within the notebook, and this is how they are implemented. But again, they will only be a subset of all the commands that are usually available within that library. So if you run it on idle or any other IDE, you'll have access to much bigger things, and especially if you then actually compile that code using Bash, then you'll get even more access to those things. So as I told you, I do a lot of simulations of how a neuron behaves, how a heart cell behaves. And the way we simulate those systems is using systems of differential equations. Systems of differential equations can become very computationally expensive. So what we're going to try to do is just approximate a very simple function, the y equals x squared function, using its derivative, which is going to be y prime equals to x. And for that, we're going to use a very simple method to numerically solve differential equations called the Euler method, in which we have to start with a value that we know for x squared. And then to calculate the following value, we take that same value and we add a step size that we have determined times the derivative of the function. That's all what we are going to try to do. This is a very simple method. It's not very used in our actual scientific environment because it's very imprecise. Very quickly you accumulate huge errors, and I'll give you an example of that. So what we're also going to try to do is when we run this function, we want to determine the minimum step size for the result to be within a specific tolerance that we are specifying as 1 to the minus 5. And we're just going to run it for 1,000,000 points. This will allow us to better compare like how long different functions take in running 1,000,000 different points at every single step. But because we're running 1,000,000 points with different step sizes, the final number that we're calculating is going to be changing, but we are not gonna care about that. The question is like, if you evaluate 1,000,000 points, how long does it take you to find the minimum step size for the difference between the approximation Euler, the derivative, and the actual function at the last point? Everybody clear on what we're going to try to do? Any questions? Okay, then let me just switch to the Jupyter Notebook. We get it. And so you'll see the notebook that you had in GitHub, they had not had the cells run. Here I've run them just because some of them will take a few seconds, and it might get very awkward if we have to all sit here in silence waiting for it to run. But basically, this is my definition of the function we want to approximate. We get 1,000,000 numbers, and then we're going to calculate their squares. We are also going to take the first one of them and run the Euler approximation for 1,000,000 more points. And at the end, we're going to calculate what's the difference between this point squared and the last point of that approximation. And we return the absolute value of that difference. And just to give you an example of how errors accumulate within this function, by the end of 1,000,000 evaluations with a step size of 1, there is an error of 5 times 10 to the 11, which is 500 billion between doing 1,000,000 square and the approximation using the Euler. So it's a huge difference. And that's why we have to keep reducing the step size until we actually get to a difference we can tolerate. So we're going to start running in a while loop these approximations with given step sizes. And if our difference is above that tolerance, then we are going to divide the step size by 10. And we're going to continue iterating until we find the step size that gives us a good tolerance. And we are printing at the end, outside of the while loop, the step size that we find. I want you to notice a few things. There's 2 for loops in this function, and we're adding another level of iteration here with this while. So within this while, you're going to have 2 for loops. That's what's going to make our computations very intensive, and is going to create the delays that we're actually going to be studying. And if you run this one, if you run it in your computer, you'll probably get different numbers. Depending on what other things I'm running in my computer, I get different numbers. But in general, we see that without any optimization, just using basic Python code, it takes 10 seconds to find what's the best step size that we get. And we see that the step size is 1 times 10 to the minus 9. So let's just write it here. That basic Python takes 10 seconds. If we use Cython, which is a way to compile Python code to see, everybody knows what Cython is? Okay, so I don't have to tell you how it works. From what I understand, it also tries to compile this within the Jupyter Notebook and then run it, and it shows you the difference. You're going to have a lot of functions within Cython, but in the Jupyter Notebook, you're basically limited to one thing, which is going to be do static typing. And the static typing is going to happen as the cdef in case you're defining a variable and you define the type. You have float, int, you have list. You cannot use the cdef for when you try to do enumerations or iterations like this. And for that, before in the Jupyter Notebook, you have to load the extension Cython and define your function within a cell that has the Cython magic. And if we run that, again, we're going to do the time it with the same code we had before. All we did was Cythonize the function, the error Euler function. This brings down the execution time to 599 seconds per loop, or 6 seconds per loop. Let's just keep it at 599. One question that I've had before is, okay, but maybe it was the first time that it was compiling the function. Maybe if it already compiled it, it's going to be able to do it faster. So if you decide to run it again, you're going to see that the execution that you get is pretty much the same. In this case, it was 598, and that's because the compilation is happening when you run this cell. Another question is, could we time while trying to do this within a Cython cell? And have you guys ever tried to combine two magic commands in the same cell? It doesn't work. You can only pick one. So if we wanted to get this timing, we could not optimize this while loop using Cython. Okay, but if you look at the code, you're going to say like, yeah, but your code is not really optimized by itself, which is what you usually do. Like when you're writing a program, the first thing you want to do is write it in a way that takes advantage of the data types and the libraries that the program always has, right? And because of the definitions of those lists, many of those lists which could turn into NumPy arrays. So it should be valid to say, why don't you use NumPy within your code? So we can write a new version in which we are using NumPy to create different arrays, NumPy arrays that are much faster than lists. And let's see how that is gonna execute. And you can see that here we change the range from before to a NumPy range. And again, if you run it just with the same time it, what you end up getting is an 835-second performance, which is an improvement compared to the 10 seconds that we get. Now, I'll tell you that many of these performances are going to be very dependent on the state of your machine. Anything that you have running on the background will definitely impact them, how they're happening. Nowadays with containers, when we can always spin up a new virtual machine with exactly the same state over and over again, I think you'll be able to get some consistency in the performance that you can get. But if you try to run it on your laptop, it's going to vary a lot. This particular one, I've had it change between 7 seconds, 835 seconds. It's always worse than Cython, but this is actually very close to the 10-second mark that we had with the irregular Python. One thing, did you guys hear yesterday at one of the keynote speakers when the person from Continuum Analytics was saying how a lot of things are already optimized on the background when you run Python within Anaconda? So one of the things that I wanted to check with them is like, well, if all this optimization is happening in the background, when I try to do these kind of things, I'm not seeing a big difference. Is it because it's already optimized? So is it worth it for me to still try to keep optimizing my code? And what the Anaconda representative told me is that you should still always try to optimize your code, because the level of parallelization and optimization that they are able to do without knowing the exact specifics from your code, it's always going to be very general, very initial. So you can still try to get these earnings. Now, keep in mind that we are trying to run something that just fits in my laptop. We're only testing 1 million samples at a time before doing the next iteration. So as you start growing in scale, and especially if you're trying to do data analysis of a huge data set, all these things will start, a lot of them start approximating ON performance, depending on the specific algorithm that you're using. So with enough sizes, even these small changes will accumulate and give you a big difference in performance. Another optimization that we have available is the SciPy library, which has specific modules for integrating differential equations. Anybody works with differential equations here? You guys are very lucky. I'm sorry to hear that. But in general, consider yourselves very lucky. So let me give you a quick showing of how the SciPy solves differential equations. So we have a specific class that when we define one function that just has our derivative, we provide some initial conditions, you instantiate the ordinary differential equation class with the function that you have defined, you set the initial values, and then it creates two objects, solver t and solver y. T is going to be the dependent variable, y is going to be your independent variable. Y is going to be the y in our original equation of y equals x squared, and t is going to be the one that corresponds to the x. Okay? And if you call them, you're going to see that they start with the initial conditions that you provided. If you input a new value to that object saying solver, call the method integrate, is going to return. If for an x of 20, I can integrate it to a final value of 400, which corresponds to 20 to the square. So notice how we just can input our values, and it's going to do a very close approximation, even starting with the same definition of the differential equation that gave us huge problems when we were running the plain Python. And it's because, again, this library is highly optimized to solve these problems. So you can say, like, well, then we don't need to find a step size. We can just put, I integrate 1 million and find if the answer is the same one as we get doing 1 million to the squared, which is fine. One thing to keep in mind is that solver y does not take NP arrays as input. So let's just still test it by running it 1 million times, each time putting a new number into integrate. And again, I'm showing you here how that's going to be implemented. And basically, we're just having our array of numbers from 0 to 1 million. We find the square numbers, and then we're going to run the solver integrate, inputting each one of these numbers, and we'll see what's the absolute difference. Based on what I just showed you, what would you expect that absolute difference to be? It should be 0, right? Because it should be able to tell, like, oh, if you give me 1 million, I'm going to calculate exactly 1 million squared. And this time, we're not going to try to find a specific step size, and I'll tell you why or you'll see why we're not doing that. We're just going to run this solver integrate 1 million times and see what we get. So we do this time it solver, print this function that we just defined, calling the integrate 1 million times, and you find that we have a difference. It's very small, but because of the numerical representation of these huge numbers that are not exact in the computer, we start accumulating very big differences at the end. Still, a difference of 0.004 is above our level of tolerance, but is way better than the 5 times 10 to the 11th that we were getting originally with the initial Python code. And notice how this one, is not very different from the 10 seconds we get with plain Python, but with this you didn't have to find what a small step size would work best for you in terms of getting a very good exact result. You can always input a smaller step size and see what happens. And you see that the performance doesn't change that much, but the precision gets much better. So that's the advantage of those differential equation solvers. So this is going to be true in general of SciPy. Do you guys use SciPy a lot? So whenever you use SciPy a lot, just keep in mind that in terms of the performance time, it won't change that much. So it will make you get the results faster of just having to code once and not trying to optimize for those hyperparameters like the step size in this case is. But it will also give you very exact results. And that's a big advantage of SciPy. So that one we had 9.69. So Cython compiles Python code to C and tries to run that C code. Now, has anybody used Numba before? How do you like Numba? It's great. So, do you understand what Numba does with the Python code?
Great thing is you don't have to.
Yeah. So it's hard to argue with that. And just because I'm up here, I felt compelled to try to figure out how Numba works. So I'll tell you guys what I understood. But if anybody, as I said, not a computer scientist, if you really understand it much better, feel free to raise your hand and give us a better description. And whereas Cython compiles to C code, Numba takes advantage of the low-level virtual machine and tries to use that, takes the Python code, moves it to the low-level virtual machine, and from there is able to optimize it to get to machine code. It works specifically good, according to the documentation, with NumPy, and specifically taking your raw Python code, detecting areas that might work better as a NumPy object, turning into that NumPy object, and then optimizing it at a low-level virtual machine. Anybody has heard anything different? So then let's just go with that. And as you mentioned, Numba is super easy to use. So Numba is already, when you install Anaconda, and in case you haven't upgraded Anaconda in a while, there's been a lot of packages that now come directly in Anaconda, so definitely do an upgrade if it has been more than a year since you do. But you can just call from Numba this function JIT, then you say, this new function is going to be the JIT version of my initial function. That's all you need to do. And that you just run this new function. And we get pretty much the same results. Notice how we've always been getting 1 times 10 to the minus 7, 1 times 10 to the minus 9, which I just think it's a matter of the representation of such small numbers. But now look at the performance time. And you didn't have to do anything. You wrote the code just the way you know how to do it. And then go send it to JIT, and that's it. You run it, and now we have 471 milliseconds compared to 10 seconds that we started with. So if you haven't used Numba, I highly recommend that you do it. There's another way to do it, and instead of doing this, you can just have your same code that you had before, and in the cell you put the decorator @JIT, and then now the function that you write in that code block will be defined as a Numba function. But again, when you go to time it, you can just call it the same name you had there. So it's very easy to use. What if one caution that I will give you is that, remember, in this plain Python code, we were starting with lists. And sometimes in my experience, Numba has given me issues accepting lists. This is not the time. I haven't been able to figure out when is it going to give you an issue for having lists. When is it going to accept them? I don't know if you've had the same. Yeah. So just keep that in mind. If you try to run your code and it gives you a problem, my experience is first let's try to find if there's a list. If there's a list, try to get around it, and then it might work. If you run it not like this, but with the decorator at JIT, the performance is the same. So you don't have any difference in terms of that. So let's try now to use that JIT compilation with some of the other models that we had that can get faster. So I tried to do with the Cython one, it doesn't work. You cannot combine Numba with Cython. Let's try with the NumPy. And what we get is that now the performance degrades a little bit. It's still super fast, but it definitely has degraded to 100 milliseconds more. And I haven't seen the documentation that says like exactly why this might happen. From the documentation, one possibility is that because Numba tries to take your raw code, say which parts can I already optimize as a NumPy object. If you have those NumPy objects there, then you're not going to be able to take advantage of that step, and there might be some conflict in like, oh, you already have some NumPy there. I might have to run something else and see if I can optimize it better or no, but that's just my impression. But again, notice how many of these things are not accumulative. The gains that you get with one technique don't add to the ones that you're getting from another technique. Okay, how many of you have done parallel processing in Python before? Okay, what kind of modules have you used for that? Okay, which other ones? MPI for Pi. Yeah, that's what you said, right? Yeah, MPI for Pi. So Dask, which there was an awesome tutorial on Friday. If you weren't here for that, definitely go check the videos for that. Oh, that's true. Thank you. There's also, on Friday, there was also the tutorial on concurrent futures. I've found that many of them require you to kind of understand some of the workings of the parallel processing. So I'm just going to tell you about the IPy parallel, which I think is like the gateway for trying to start working with this parallel processing in Python and trying to make sense of things. One thing that IPy parallel requires is that first you have to start the IP cluster object in your terminal. And let me show you how that looks. So in your terminal, you just enter IP cluster start, and at the end, it's going to tell you how many engines it starts. It will start one for each of your cores. So if you, like me, had no idea how many cores your machine had, this will tell you exactly how many are there. Then you can go back to the Jupyter Notebook, import from the IPy parallel library the client object, instantiate that object, and this instantiation is going to be able to create a view. So this V is going to be that view of that instance, and we can say we want to create a view of how many of those cores. Okay, and if you just do like this, it will create a view for all the cores, which we're going to do in this case because we are going to want to send portions of our task to each of the cores. But you can say, no, just show it to me for the first core or the second core. And to confirm another way to confirm how many cores or engines you have running. In theory, it should be one engine for each core. You can do rc.ids, and we return 4 numbers for the 4 cores in my computer. The part that I personally always have trouble with is, I know I want to run this in the different cores, but many times that requires my code to be changed to make it parallelizable, so that only a certain portion will go to each of the cores, and I don't end up running like in the beginning. I would always end up running the same code 4 times in the different cores and getting the same answer from all of them, which kind of defeat the purpose of the whole thing. So here what we're going to do is, again, we're going to send our initial function to the different cores, but when we send it, let me say it here. When we send it, we're going to attach to it as inputs 4 different numbers, which is going to be 4 different step sizes, 1 for each core. Each core will then do run the simulation, find the difference at the end, and return that difference. And because each core should get a different initial step size, then we'll be able to compare if we are able to find one that gives us our desired tolerance. The function that we're going to use is called v.map. So from our view, we use the map method, and as inputs for that map method, we have our function and the different step sizes that we want to try. The step size, it's an array of 4 numbers. So now this variable async job will know that it has to take this function, take one of these numbers, and send it to a core. Then take the function, the second number, and send it to the core. Because this is going to be an asynchronous performance, we manually have to collect those responses. And we're going to do with the get method from the async job object. And then we find our difference by the minimum of those 4 results that we get. Each core returns a given difference. Let's try to find what's the minimum of that one, and that's the one we check to see if it's above or below our tolerance. When we now print the step size, because step size now is 4 different numbers, we're going to have back an array of the 4 different numbers. Notice how here we're not determining exactly which of these 4 numbers was the one that achieved the desired tolerance. And the reason why I didn't do that part here is so that we can compare the codes better. Like this is closer to that all the other codes are doing better. But also notice how when I do the parallelization, then starts adding some other steps, some other additional steps that we need. And when we run that, we see that we get 581 seconds, which is roughly half of the time that our raw code has. But if we have 4 cores, why are we not getting only a fourth of the time? And part of this is that there is an overhead for doing the parallelization. So you don't get those exact optimizations that you were trying. You can try to do then other portions like optimizing with NumPy within the while loop that makes the call. And then in that case, again, you are combining some NumPy optimization with parallelism. You get, again, the 10 seconds that you had in the beginning, because it's very hard to combine these different things. But we can also use NumPy inside the function that is doing the calculation. And this combination I just wanted basically to show you how you can, within the course, import a library. And using IPyParallel, you do the magic percentage px and then import whichever library you want into those cores. Because we are not defining which cores we want to import it, it's going to import it in all of them. But I'm giving you here some syntaxes in case you want to import it to a specific core, or when you want to run not just one line command, but code blocks, how you have to do it. So let's go see what's the performance of that. And it's 5 seconds per loop. Again, we're able to bring it down, but it's not so different from what we were getting with the parallel. It's almost 1 second less than what we were getting with the parallel alone. We can also do synchronous execution, in which the only difference is you don't have to manually collect the results at a very big view level. And I'm giving you the syntax here. Is the same thing you had before. Now it's just v.map underline sync, but everything else is the same. And you don't need to do sync results.get, because that's implying this synchronous execution. But the performance is, again, pretty much the same. So there is not much difference between asynchronous and synchronous within the Jupyter Notebook, and as long as you're not running a lot of other processes within your machine. And finally, let's do Numba with parallel processing. And let's see what we get. And again, the way to do it is very easy. Just take the parallel function that we were using, send it as an input to the JIT function of Numba, and run that new function that you defined with that. And what you're getting now is that the execution is 1.2 seconds. Still worse than what we got initially with Numba, and it's because now the overhead ends up being, the overhead of sending it to do parallel processes ends up being more expensive than when you were just running your code by itself. But that's still 1 order of magnitude better than what we started with. And that's all I had to show you guys. If you ask, my recommendations is, of course, always benchmark your code, find where the bottlenecks are, try to optimize all that part, all those things that, all those good software practices that you guys know about. But once you have found that out, I would recommend start with Numba. Don't jump into parallel processing. Depending on the size of your inputs, you might have to go to parallel processing. There's a lot of different libraries coming out for parallel processing in Python. I haven't seen a good comparison benchmarking all of them. I personally find iParallel to be very straightforward and intuitive, but it might not be, and I think that is definitely not the one with the best performance there. But as you get comfortable with that, definitely start moving to things like multiprocessing, concurrent features, MP4Py, Dask, and check those. And I'll take any questions if you have any.
Do you know when the overhead cost is mitigated by the number that you're sending? Does parallel ever get faster than the
Yes. So when the overhead in sending to parallel processing doesn't change that much, but with your input size. So if you have a huge input at one point, even that overhead becomes a very small part of the whole process, and it becomes worth doing the parallel processing. And especially now with cloud computing, I think that's going to be very important to keep in mind.
Then if you get the new 72-core processor.
If you have something like 72-core processors, that's definitely cool. And that's the advantage with cloud computing, that the sky is the limit. It's only limited by how much can you pay for those machines. Any other questions?
Do you have any idea in other computation other than solving the differential equation, like solving some matrix like SVD or PCA, stuff like that? Can you give me any comments on which method is faster?
So the question is if I have any benchmarks on other type of computations different than just solving differential equations, right? The answer is I do not. My objective was just give you some syntax that you can use to then go and try to apply to your specific problem. So I don't have on any other thing. Sorry. Do I have time for question?
On the parallel one, you started something in the terminal. What was that again, and where do you install it from? Is it like OS specific? Is that part of Python?
Oh, that's a really good question. So on the terminal, when we start, oh, hold on. Sorry? Yes. So the question is, on the terminal, when we do this, where is the IP cluster starting? So you can install it with conda install. You can do it with pip install IP cluster. And then what it does is just going to start engines for each of your cores, because when we had the tutorials on Friday on parallel processing, I didn't see that that was necessary with Dask or future concurrents. They might do it behind the scenes. With IPy parallel, you have to specifically start those engines. And that's what it was. Any other questions? Okay, well, thank you all for coming.